Hello dear students, in the previous session we were discussing the concept of Hahn-Banach theorem, which is a part of your extension functional, right? So what we were having a mapping f from m0 to n, where we were discussing the cases for n, that is, one is real normed linear space, another one is complex normed linear space. Real part was over. We were proving for complex normed linear space, right? So what is our m0 here? M0 is a subspace which will be in the form of m union x0, and we will define that space as x plus alpha x0, where x belongs to m and alpha is some real value. So why I have taken m union x0? Because x0 is the point which does not belongs to m, but it belongs to m0. That's why we defined our m0 in this way. So we were proving for the case of complex normed linear space. In that we proved that f0 is linear, right? I have proved the theorem separately for vector addition and scalar multiplication. I can prove in one more way, that is, if I choose alpha, since alpha is complex here, obviously it will be in the form of a plus ib, right? So now I can define this as where your a and b are coming from real line r. So f0 of a plus ib into x will be equal to g0 of ax plus ibx minus I into g0 of minus bx plus iax. How can I define this? Because I know that f0 of x is equal to g0 of x minus I into g0 of ix, right? So in this way we can write f0 of a plus ib into x as g0 of x. In the place of x we have ax plus ibx. Similarly, in the place of ix, I have to substitute this. So here I have written after multiplying this imaginary I with this whole term. Okay. So now we can write this as f0 of a plus ib into x is equal to a g0 of x plus b g0 of ix minus I into minus b g0 of x minus I into a into g0 of ix. Okay. So now I can take a plus ib as common. So if I choose a plus ib as common, I will be getting g0 of x minus I into g0 of ix. So now what is g0 of x minus I into g0 of ix? This is nothing but your f0 of x, right? You can observe here. So your RHS part will become a plus ib into f0 of x. In the LHS we have f0 of a plus ib into x. So from this we can say that f0 is linear, right? So now I have to prove that f0 is bounded also. For that, first I will consider a point x which belongs to the space m0. This is some arbitrary point. Okay. So we can define our f0 of x function as r into e power I theta. Since we are in complex valued function, we are defining f0 of x in terms of e power I theta. This is nothing but cos theta plus I sin theta, right? So it will be in imaginary form. So we can write in that way, where your r will be greater than or equal to 0. So now if you choose your mod f0 of x, this will be equal to r. So this is equal to, I can write this as e power minus I theta into r into e power I theta, because since bases are same, if I add the powers it will be e power 0. E power 0 is 1. So mod f of f naught of x means you have to take modulus of this, right? So what is mod e power I theta? You can write this as cos theta plus I sin theta, and modulus of cos theta plus I sin theta can be rewritten as square root of cos square theta plus sin square theta. The value of this is 1, right? So you will be getting only r. So I am writing r in terms of exponential only. For that purpose I have written e power minus I theta into e power I theta into r. Okay. So now if you observe here, what is r into e power I theta? It is f naught of x. So I can write my modulus of f naught of x as e power minus I theta into f naught of x. Or we can write this as f naught of e power minus I theta into x, because f naught is linear, right? Since the function g is less than or equal to f, I can write this as mod f naught of x will be less than or equal to mod g naught of x into e power minus I theta into x. We have seen this in the previous session, right? F of x is nothing but g of x plus I into h of x. So if I choose only g of x, obviously it will be less than or equal to your whole function f of x. Using that concept, this term will be less than or equal, greater than or equal to g. If you are getting confusion with f naught and g naught, you can do one more thing. You can assign this e power minus I theta to g naught, so that here your mod f naught of x will be less than or equal to mod g naught into e power minus I theta into x. Make a small correction. In the previous session we have seen that g naught is equal to g on m and f naught is equal to f on m, right? We have seen these two cases in the previous session. We can write this because we have already proved that f naught is linear on m naught. So there will be an extension for f naught, and in space m, from the given lemma we can write that g naught is equal to g and f naught is equal to f on m. So from these two we can write f naught is equal to g naught, right? So now I can rewritten this as, I will repeat this once again, just go through this carefully. So first what we have done, we have taken f naught of x is equal to r into e power I theta. If you take mod on both sides, you will get mod f naught of x as r. So again I am writing my r in terms of imaginary part, that's why I have just multiplied e power minus I theta and e power I theta here. So since the bases are same, you can add the powers, you will be getting r itself. Now your mod f naught of x can be rewritten as e power minus I theta, I will retain as it is, and r into e power I theta is nothing but f naught of x. So since f naught is linear, you can write that f naught of e power minus I theta into x. Okay. Now since f naught is linear in m naught on m naught, and from the statement of the given lemma we can write g naught is equal to g and f naught is equal to f on space m, not on m naught. I am not writing on m naught, this is on m. Okay, so since g naught is equal to g on m and f naught is equal to f on m, from these two I can say that f naught will be equal to g naught. Now let's continue with this part. So now I can write mod f naught of x will be less than or equal to mod g naught into e power minus I theta into x. So this will be less than or equal to norm g naught into norm e power minus I theta into x. Again you can split this as norm g naught into mod e power minus I theta into norm x. So here it is mod f naught of x, right? This will be less than or equal to, we know that g naught is equal to g, so this is norm g, and modulus of e power minus I theta is 1, so I can write it as norm x. My mod f naught of x is less than or equal to, so again I can replace g by f into norm x. So now you can observe this carefully. The value of norm x, we usually take it is less than or equal to 1, so I can write this as f naught of x is less than or equal to norm f. Since f naught is a function, I can write in terms of norm also. It makes no difference. Okay, so norm f naught of x is less than or equal to norm f of f. So from this what you can conclude? You can say that f naught is bounded on m naught. So this implies f naught is functional on m naught. That is norm f naught is less than or equal to norm f, right? This is one part of the proof. Now from case 1 we have already known that f naught is extension of f, right? F naught is extension of f means I can write norm f naught is greater than or equal to norm f. So now from star and double star we can conclude that norm f naught is equal to norm f. Till here we will prove the boundedness property. Using this property I can say that f naught is functional on m naught. That is nothing but from this only we can write your star condition, star inequality. Norm f naught is less than or equal to norm f. So we from case 1, that is we have discussed in real normed linear space, right? From that we can say that f naught is extension of f. It is already proved, so you need not to prove that part again here. From that I can say that f naught is extension of f, so that is nothing but norm f naught is greater than or equal to norm f. Using these two inequalities I can prove that norm f naught is equal to norm f. So this ends the proof of your lemma. Let's make a short note of this now. So what all the things we have proved in order to prove Hahn-Banach theorem? We have used the lemma. In that lemma, n act as real normed linear space and complex normed linear space. For these two things we have proved the cases which they have given. So that is nothing but, if I consider this whole space as n, and if this is the space m, I can choose one point in m. So the mapping will be in real or complex plane. This is f of x, right? If I extend this space to m naught, till this part we have done. Now I have to prove for whole space n. So if I choose a point, say x naught, this x naught belongs to m, right, as well as m naught, but we have chosen a point x0 which belongs to m0 and does not belongs to m. So again, if I take the mapping, it will be f0 of x. So since this point x belongs to m as well as m0, after mapping also we can say that f of x is equal to f0 of x in m0. Now we are speaking about the space m0. So this part of the proof is over. So from this we can conclude that norm f is equal to norm f0. Now let's go back to the Hahn-Banach theorem. Let's prove the remaining part in your Hahn-Banach theorem. From the statement of Hahn-Banach theorem, what we supposed to prove? This is the statement, that is, let M be a linear subspace of a normed linear space N. Let F be a linear functional on M. Then F can be extended to a function F defined on the whole space N such that norm F is equal to norm F. This part of the proof is left out to prove, right? So in order to prove this part, I will be using two main concepts, that is, one is partially ordered set, another one is Zorn's lemma. You have studied both the topics in your previous semesters. So let's see the partial ordered set definition first. When you can say a set is a poset or partially ordered set, if it satisfies three conditions. What are those three conditions? One is reflexive, another one is anti-symmetric, and the last one is transitive. So any set which satisfies these three conditions, then you can say that particular set as a partially ordered set. What is the condition to satisfy reflexive? It is if I choose some element x, if x is less than or equal to x, you can say that it is reflexive. For anti-symmetric, if x is less than or equal to y, and if y is less than or equal to x, this implies x is equal to y. This is nothing but anti-symmetric. Similarly, transitive is if x is less than or equal to y and y is less than or equal to z, this implies x is less than or equal to z. This is how you define your reflexive, anti-symmetric and transitive conditions, right? So now this x, y, z belongs to some set A, and I can say this A as a poset or partially ordered set. Now how do you state your Zorn's lemma? Zorn's lemma states that if I choose any non-empty set, that is every non-empty poset in which each chain has an upper bound and that upper bound has a maximal element. So in order to prove Zorn's lemma, in order to state Zorn's lemma, we will consider poset. We have already seen the definition of poset. So every non-empty poset in which each chain, that means your poset forms a chain in that each chain has an upper bound, and for that upper bound has a maximal element, right? This is how we define our Zorn's lemma. Now I will use these two concepts in order to prove the remaining part of your Hahn-Banach theorem. First I will consider P as a set of all bounded linear functional and which is the extension of your F. Okay, we are considering a set P, and this set P consists of all bounded linear functional, and for all bounded linear function it has a extension of F. So let's say we have some G1 and G2 points which are coming from P. In the whole set we are choosing some 2 points, that is G1 and G2. So if I define partial ordered set, I can say that from there is a relationship between G1 less than or equal to, I can write this relation from the definition of partially ordered set, right? So using the definition of partially ordered set, we can write G1 is less than or equal to G2 if and only if the domain of G1 is contained in the domain of G2. Right, I repeat. So we are considering 2 points from the set P. In that, since P is a partially, in order to say P as a poset, I have to prove that G1 is less than or equal to G2 if and only if domain G1 contained in domain of G2, or I can say that G1 is equal to G2 on G. Right? So now, if you can compare any two elements in a poset, means if we are comparing, you can observe here I am comparing G1 and G2. If you are comparing two elements in any set, poset means it forms a chain. Right? So I can write that chain as A is equal to G0 less than or equal to G1 less than or equal to G2 less than or equal to, and so on. This is a chain in P. Observe carefully. First, what we have done, we have considered a set P, and this set P consists of all bounded linear functionals, which is the extension of F. Now, in the whole set, I am choosing some 2 points G1 and G2. If I have to tell this as a poset, then I should compare G1 and G2 if and only if the domain of G1 contained in domain of G2 and G1 is equal to G2 on G. This is the condition in order to say that P is a poset now. So now, any two elements, if we are comparing any two elements in a poset, means it forms a chain. I will write that chain as A is equal to G0 less than or equal to G1 less than or equal to G2, so on, and this is my chain in P. So if you take the union of these chains, okay, it will be a least upper bound for A in P. So if you take the union of all this, you will be getting Gn, right? And that Gn will be the least upper bound for A in P. Now from the definition, from the statement of your Zorn's lemma, it has a maximal element. For this least upper bound, we have a maximal element. Since we are discussing about functionals and the set is consist of functional, I will say that maximal element is the maximal extension. Okay, the maximal element is nothing but maximal functional here, or I can say that maximal extension, and I will that extension as F. So what we are doing, we have taken the union of this whole set, the chain, and we are telling that according to the Zorn's lemma, it has a least upper bound, and that least upper bound contains maximal element. Here that maximal element is nothing but maximum extension, say F. So now if you use your previous lemma, from the previous lemma you can say that norm f is equal to norm f, because here if I extend this whole space till n, obviously that will be your maximum extension, and we are calling that as f of, this is x1, this will be f of x1, right? So if this is the maximum extension, then I can say that my f of x1 is equal to f naught of x, and this is equal to f of x, right? So using previous theorem, I can conclude that norm f is equal to norm f. So this is how we prove Hahn-Banach theorem. So basically there are 3 points. One is, in order to prove Hahn-Banach theorem, you have to prove the lemma. In the lemma we have 2 parts. One is real and another one is complex. Then you will conclude this lemma, you will come to Hahn-Banach theorem. There you should be knowing 2 conditions. One is definition of poset and another one is Zorn's lemma. So using these 3 concepts, you will conclude the Hahn-Banach theorem. So this is all about Hahn-Banach theorem. Thank you.